Hi, today we're going to talk about solutions. You've already learned something about solutions earlier in general chemistry, but what we're going to talk about today is we're going to start thinking about solutions not as something that we just use in lab, but we want to think about what's going on with them on a molecular level, and also what an influence that molecular structure has on the energy of a solution. So a quick review of what a solution is. First of all, it's a homogeneous mixture. In other words, everything has the same concentration at any given place within the solution. So a solution will have more than one component, being a mixture, and the most common of those components we're going to call the solvent, and the less common components we're going to call the solute or solutes if there's more than one. When we think about solutions, we usually think of aqueous solutions, stuff dissolved in water, like dissolving lemon juice and sugar in water to make the solution we call lemonade. But the truth is that solvents can be any state of matter. So you can have gaseous solutions where you have one gas dissolved in another, and geologists talk about solid solutions when they're talking about minerals. So there's all sorts of solutions in any state of matter, and the solutes can also be any state of matter, solid, liquid, gas, and more importantly, they can't be removed by physical methods. So you can't filter them out, you can't centrifuge them out. It is very hard to get things out unless you actually change the conditions of the solution. So one of the things you may have observed in the first part of Gen Chem was the whole concept of the enthalpy of solution, or people sometimes call it the heated solution. So basically you dissolve something in water and there's no chemical reaction going on, but the mere fact that something is dissolving in that solution actually causes the temperature of the solvent to change. And this is a phenomenon that gets used, for example, in hot packs or cold packs. You basically, you break that thing that's inside, you feel that pop, and then as the things mix, it produces heat or it turns cold. So we're going to talk about why that is. But first, when you talked about thermochemistry earlier, you probably learned that breaking bonds takes energy and forming bonds releases energy. And that is actually basically what is going on here. When I tell students that, sometimes they get a little dubious. They're like, yeah, but there's no chemical reaction going on. It's just dissolving. What bonds are you forming or breaking? So let's look at a molecular picture of something going into solution. And so I've decided to make a fairly common solution that you're pretty familiar with, basically a saline solution, sodium chloride. So on the left here, I've got a sodium chloride crystal, obviously very, very simplified. There's usually far more atoms than that. And on the right, we have some water. So what we want to do is we want to dissolve the sodium chloride in the water. And so what is going to happen? Well, let's think about this water. Water, as you learned earlier, has a whole bunch of hydrogen bonds that hold it together and give it its many properties. Additionally, the sodium chloride is being held together by something. What is it being held together by? By ionic bonds. So when you're creating a solution, one of the things you need to do is you need to take apart that solid solute so that it can go into solution. So the sodium and chloride ions are going to come apart from each other. That in and of itself is going to require energy because we're breaking bonds. The other thing that's going to happen is that we are going to be breaking intermolecular forces that hold the solvent molecules together. Why would we have to do that? Because those solute molecules are basically going to go into the middle of the water and have water molecules all around them. So in order for that to happen, we need to make room. And now finally, now that the sodium and chloride ions are in place, now we can do the third thing, which is to form new intermolecular forces between the solute and the solvent. And you'll notice earlier when I was shuffling things around, some of the water molecules spun around, because what's going to happen is that the sodium ion, which is positively charged, is going to attract the negative end of the dipole on the water molecules. And the chloride atom, which is negatively charged, is going to attract the positive part of the dipole, which is a water molecule. So they will arrange themselves, and then they will form new forces, which in this particular case are ion dipole forces. So back to what I said earlier about energy being released or absorbed. When a solute dissolves, you are breaking bonds and you are forming bonds. They're not covalent bonds, they're not ionic bonds, but they are intermolecular forces. And from this, we can calculate the molar enthalpy of solution, also known as the heat of solution. And that's basically the total energy absorbed or released when a solute dissolves in a solvent. And so we can think about this, think back to Hess's law, we can think about this as a series of steps, as I laid out earlier. First of all, you start where you have the solvent molecules separate from the solute molecules. In this case, we have salt off to the side of a beaker of water. Then we have to start pulling things apart. So we have to separate the solute molecules. To do that, we have to put energy in that puts us up to a higher energy state. Next, we're going to separate the solvent molecules from each other. That also requires an input of energy, so we're going to go up to an even higher energy state. And then what we're going to do is we're going to put the solute into the solvent. It's going to form new intermolecular forces, and as it releases energy, it brings us down to a lower energy state. So how much energy is released or absorbed by this process? Well, it's the difference between the initial and final energy. So that goes along with what you learned about Hess's law. Will it be exothermic or endothermic? Well, again, we have bonds being formed and bonds being broken, right? What's being broken? The bonds between the solvent molecules and the bonds between the solute molecules, whatever kind those are. And keep in mind, these might be actual bonds like ionic bonds, or they could be just intermolecular forces. So when we say bonds, we mean any sort of force that holds things together. In terms of bonds forming, the only bonds that are going to be forming are going to be between the solvent and the solute. So we're going to compare the energies for these, and I'm not going to go into numerical detail here, but you can think about if a bond is really strong, it requires a lot of energy. So if you have really strong bonds between the solvent molecules, it's going to require a lot of energy to pull them apart. If you have really strong bonds between the solute molecules, it requires a lot of energy to break them apart. If you form strong bonds between the solvent and the solute, then you get a lot of energy out. But what if they aren't strong? What if you're talking about weak bonds? If you have weak bonds between your solvent molecules, or if you have weak bonds between your solute molecules, then it's really easy to pry them apart. You don't have to put a lot of energy in. If you have really weak forces or bonds that form between your solvent and your solute, then you don't get much energy back when you put them together. So let's try and consolidate those concepts into a very simple way to remember things. If you're breaking strong bonds, which requires a lot of energy input, and forming weak bonds, which means you get hardly any energy out, then you're going to have an endothermic reaction. You put in more than you get out. If you break weak bonds, which requires very little energy input, and you form strong bonds, which means you get a lot of energy out, then you're going to have an exothermic reaction because you get a lot of energy out after a very small amount of energy in. So overall, energy is going to come out. We have talked about the thermodynamic properties of a solution. What I want you to take away from this is that many properties of solutions, which include thermodynamic properties, but it's not limited to that, they're really dependent on the intermolecular forces. So we're definitely going to be talking a lot about intermolecular forces as we talk about the solution properties in this chapter. I hope this was helpful, and I will see you again soon.